This video deals with the recognition of graphs, which simply means the following. You'll be given a graph, the plot of a quadratic curve, for instance. You'll be given a plot, and you could be given its root, so the coordinate of the point of intersection with the x-axis. So let's say this is 2 and this is minus 2, for instance. Now, you're given a curve and you're given its roots. You're now asked to determine the equation of this curve using the given information. So that's the same thing as recognition. So you're trying to recognize which graph this is. You're trying to say, oh, this graph, the equation belonging to this diagram you've been given is so and so. So that's the whole essence of this section. So before proceeding to actual recognition of graphs, there are a few things you need to know, and I'm going to lay it down. Now, here's a quadratic equation, the general form of a quadratic equation. Now, one thing to know is that the equation y equals ax squared plus bx plus c has the same roots as the equation y equals n times ax squared plus bx plus c. Now notice, this quadratic equation is the same. Well, this bit is the same as the bit here. All we're doing is saying an n here represents a real number. It's just a multiple of what I'm trying to say. The right hand side of this equation is just a multiple of the right hand side of this equation. So what I'm trying to say is this equation has the same roots as this equation. So if I have an equation like y equals 2x squared plus 3x plus 1, I'm trying to say that it has the same roots as the equation y equals n, where n is any number, times the same 2x squared plus 3x plus 1. So you need to accept this and use this fact to help you determine, basically to help you recognize graphs. But how? Let's sort of, I don't want to prove that an equation of this form has the same roots as an equation of this form, but I'm going to just demonstrate that it does. There is a proof, but it's beyond the scope of the y course. So I'm going to give you an example equation. I'm going to give you the equation y equals x squared minus 4x plus 4. This is an equation. Now, I'm going to say that this equation has the same roots. What I'm telling you is that this equation has the same roots as the equation y equals n times the same thing. Okay. So, let's do the following. Where n is, okay, I need to specify that n is not equal to 0. I think it's important I specify that. So let's test the case when n is 1. Let's determine the roots of this equation when n is 1. When n is 1, we have y equals x squared minus 4x plus 4. So basically we have this equation. What are the roots of this equation? Well, you determine the roots of a quadratic equation by setting y, replacing y with 0, and solving the equation you obtain. So for this equation, I'm just going to write it this way. I'm going to use the method of inspection, which is something we've covered already. So I'm going to quickly solve this. So what two numbers do I multiply to get 4? I want to add, get minus 4. So in this equation, we have, so remember, solution to this equation, x minus 2 is equal to 0 or x minus 2 is equal to 0. Basically, we have x equals to 2 and we have a repeated root. Now, I'm telling you that when n is 2 in this equation, we get this equation, right? Now, I'm telling you that this equation has the same roots as this equation. Why? Well, this is an equation. I'm not going to expand it yet. I'm going to just take this as the equation, and I'm going to solve for the roots. To get the roots, replace y with 0. So we get this, basically. So y has been set to 0, and I've just swapped left hand side and right hand side. This is what we have. Now, let's divide both sides of this equation by 2. I'm going to divide this side by 2, divide this side by 2, 2 here, 2 and 2 into 1, 0 over 2 is 0, so we have x squared minus 4x plus 4 equals 0. Now I need to solve this, but wait a minute, this equation is the same as this equation here, so the roots of this equation will be the same here. But remember, we started with this equation, we set n as 2, and we said, okay, this is the equation we have, we want to determine its roots. So we just went ahead to simplify the equation. At the end of the day, we ended up arriving at this same equation here. Obviously the roots will be the same because they're the same, it's the same equation. And this will happen when n is 3 as well, as you'll see shortly. When n is 3, we have y equals 3. So when n is 3 here, y equals 3 times x squared minus 4x plus 4. I want to find the roots of this equation. I'm going to set y as 0, which gives me this. Right? Now I'm solving this equation to determine its roots. So nothing stops me from simplifying this equation. Nothing stops me from dividing through by 3. And when I do that, I get 0 divided by 3 equals this whole expression divided by 3. And that gives 0 divided by 3 is 0. 0 divided by any number is 0. And 3, 1. So that just gives 0 equal to x squared minus 4x plus 4. Again, we've arrived at the same equation. Same equation. Same equation. So same roots. So I'll just go back to the main point. An equation of this form, a quadratic equation y equals ax squared plus bx plus c, has the same roots as the equation y equals n times the same ax squared plus bx plus c. So an equation y equals 3x squared plus 2x minus 4 has the same roots as the equation y equals n, where n is any number. So in this case, I'm going to let n be 4. So 4 times 3x squared plus 2x minus 4. It also has the same roots as this equation. Also has the same roots as the equation y equals 5 times 3x squared plus 2x minus 4. So now you must get the hang of it. An equation of this form has the same roots as an equation of this form. The only difference between these two equations is that I'm multiplying the right hand side by a number n, where n isn't 0. Because if n is 0, I get y equals 0. So what I've just demonstrated is that many different equations can have the same roots. Now, how a root represented graphically? You have a quadratic curve. For instance, this is just a random curve I'm drawing. Its roots are its intersection with the x-axis. So the roots of a quadratic graph are given by the x-coordinates of its points of intersection. Now, I'm saying that other graphs, other quadratic curves can have the same roots. That's another quadratic curve in blue. I'll show you another one. So this is a rough sketch. This should be parabolic shapes, but this is just a rough sketch. But the main idea is you can have different equations. So each of these lines represents a different equation, different quadratic equation. These are the graphs, and each of them intersect the x-axis at the same point. Each of them have the same roots, because the x-coordinates of these points are always going to be the same for the different equations. So what I'm trying to stress is that if you're just given a graph, a quadratic graph, and you're told that its roots are, say the x-coordinate here is, let me use a different color, the x-coordinate here is 3 and the x-coordinate here is minus 4 something. You can't just say, oh, I'm going to construct the equation because I know its roots. Remember, you can construct quadratic equations given their roots. But now I've told you, I just demonstrated that you can have multiple equations which have this same root. So, and if you construct an equation using the same roots, you're going to get the same equation. But we know that different curves have different equations. So the whole point of this section, this video, is that to point out that just being given a quadratic graph and its roots is not sufficient to determine the equation, uniquely determine the equation of the given graph. You need something else, because different graphs can have the same roots. So just by knowing the roots, you can't just construct the equations from the roots and then say, oh, that's the equation. You need something else, and I'm going to show you. So here we have an example. We're given a quadratic curve. We're given its roots. As you can see, the x-coordinates of its points of intersection with the x-axis are given 3 and minus 4. And here we're also given a point on that curve. The coordinate of this point is 4, 16. The x-coordinate is 4. The y-coordinate is 16. So my question now is, what is the equation of this curve? Now, one will say, well, I have the roots. The roots are x equals minus 4 and x equals 3. And I know that I can construct an equation from the roots simply by doing the following. So if the roots of an equation are x1. So let's call this x1 and x2. Equation can be constructed by doing the following. You're writing the following expression. This has been treated, and by simplifying this expression, you can get a quadratic equation. So in our case, x1 is -4, and x2 here is 3. Minus times -4 is +4. So we have x plus 4 and x minus 3 equals 0. So I'm going to expand this. I'm going to expand this quickly. X squared minus 3x plus 4x minus 12 equals 0. X squared plus x minus 12 equals 0. So now I've been given a quadratic equation. So now from the roots, I've constructed a quadratic equation, which potentially could be the equation of this curve given here, but we need to test it. Now we've constructed a quadratic equation given its roots, right? Now what I'm trying to tell you is, so let's take the equation y equals x squared plus x minus 12. Let's test this equation. So from constructing an equation from the roots, I got this equation. And in order to determine a possible curve, just replace the 0 with a y. That's perfectly valid. I don't want to go too much into the details. Unless you really want to know, you can ask a question and we'll get back to you. Replacing the 0 with a y gives me this equation here. Y equals x squared plus x minus 12. Okay. Now, I've been told that the point this point here with coordinates 4, 16 lies on whatever graph this is. Now, if 4, 16, this point actually lies on this equation, on the plots of this equation, it means that point 4, 16 must satisfy this equation. So let's see if it does. Now, the x coordinate of this point is 4, the y coordinate is 16. So what I'm going to do is replace x with 4 in the equation, and let's see what we get for y. We expect to get 16 if this is actually the equation. So let's try it now. When x is 4, x squared becomes 4 squared plus 4 minus 12. And we get y equals 16 plus 4 minus 12, which is y equals 20 minus 12. 20 minus 12 is 8. This is not 16. Therefore, this isn't the equation. Now, what I'm trying to tell you is that the equation has the same roots as this equation. The equation y equals x squared plus x minus 12 has the same roots as y equals n times x squared plus x minus 12. Now remember, we had the roots of an equation and we constructed a quadratic equation. The quadratic equation we constructed has these values, -4 and 3, as its roots. Now we got here, actually where we go from construction with x squared plus x minus 12 equals 0. And in order to determine just an example of an equation which has these roots, just replace the 0 with a y. And I don't want to go into the details of why, but it's true because we can test it. You can try solving this equation using the method of completing the square of the quadratic equation or the method of inspection, and you find that these are actually its roots. Anyway, moving on, what I'm trying to say is this equation has these roots, but we just found out that by testing this point, which lies on lies on this curve, we found out that this equation does not represent this curve, because if this equation represented this curve, this point which lies on the curve would satisfy this equation. This point here, 416, does not satisfy this equation, because if it does, when x is 4 in the equation, we should get a y value of 16. We replaced x with 4 in the equation and we got a y value of 8. So we know that this isn't the equation. But if you remember, I said an equation of this form has the same roots as an equation of this form. So this equation has the same roots of an equation. So we just need to determine what n is. We need to determine the value of n that will be such that when we plug in for coordinates of this point into the equation will be satisfied. So what am I saying? I'm saying the equation y has the roots -4 and 3. This equation has the root. So remember, if you look at the graph, we can see a curve. This curve is a plot of an equation, and that equation has the roots -4 and 3. Fantastic. This equation, as I've shown earlier, has the roots -4 and 3. But for a certain value of n, the point 416 will satisfy this equation. So we need an n value which is such that y is 16 when x is 4. So in order to determine this n value, I'm going to replace y with 16 and x with 4 and determine the n value that basically gives us what we want. So when y is 16, left hand side is 16, n is n, that's what we're looking for. X is 4, so x squared is 4 squared plus x plus 4 minus 12. So we have 16 equals n. 4 squared is 16 plus 4, 20. 20 minus 12 is 8. So we have 16 equals n times 8, which is 8n. So 8n is the same thing as 16. Divide both sides by 8 gives 16 over 8. N is equal to 2. This means that when n is 2, we have an equation whose roots are this, and an equation where the point 416 lies. Well, an equation which is such that the point 416 lies on its plot. So let's test this. This is the equation that we've determined, because n is 2. So y equals 2 times x squared plus x minus 12. That's the equation. Now, when x is 4, what's y? Let's see. I'm going to use a different color. When x is 4, y is 2. 4 squared plus 4 minus 12, determined as 8. Y is 16, as required. What are the roots of this equation? Well, let's see. Y is equal to 2x squared plus x minus 12. The roots are determined by replacing y with 0, and that gives 0 equals this, which gives 2x squared plus x minus 12 is equal to 0. Dividing both sides by 2 gives x squared plus x minus 12 equals 0. Now, this equation is the same equation we constructed from the roots. So we know that this equation has these roots, -4 and 3. Therefore, this curve has the equation y equals 2, basically this. Now, this is probably the first time you're seeing something like this, and I don't expect this example to make perfect sense straight away, but we're basically going to demonstrate this idea again in other examples, and by the time we're done with other examples, it will stick. Do not expect to understand it just from this example.